Now in this video lecture we will explore the main inequalities involving the Lebesgue integral. The inequalities is what will allow us to make estimates and different types of arguments. They will be extremely useful in the theory of measure theory and probability theory. Let's start with one of the most basic inequalities in the theory. It's known as Chebyshev's inequality or Markov's inequality. So in a measure space, we have a function which is an extended Borel function, and for every number epsilon positive and every number alpha larger than or equal to 0, well, equal to 0 wouldn't be very interesting. We can bound from above the probability or the measure of the set of points where the function f takes large values, larger than epsilon, or smaller than minus epsilon, of course. And we can bound it by a constant, if epsilon is constant, or something that will depend on epsilon, to the power alpha times the integral of this function, of the absolute value of this function, to the power alpha. And the proof is basically just chase the definition, start from the end and see if we can compare it with what we started with. So how can we bound from below the integral of a certain function to a certain power? How could we bound this from below? Well, this is certainly larger than the integral on omega of this function here, f of omega to the power alpha times the indicator function that f is larger than epsilon. So having a non-negative function, when we multiply it by an indicator function, this cannot be larger. So this function is comparable with this function point by point. And let us add here the point of omega. And here we can use the expression mu of the omega. That's an alternative notation for integral when we make explicit that we are defining the function to be integrated by an expression that depends on omega, right? Like here. And then we see we're integrating this function on omega. But look, there are two types of points omega here. Either this indicator is 0 and then the whole product is 0, or the indicator is 1. And when the indicator is 1, this function here is actually larger than epsilon. So in both cases, this function being integrated, in both cases, it is larger than or equal to epsilon to the alpha times the indicator that the absolute value of the function is larger than epsilon. And now we know the integral is a linear operator, so it's homogeneous. We can take a constant out of the integral. And we know it is a unitary operator, meaning we know exactly what is the integral of an indicator function. So this is exactly equal to epsilon to the alpha times the measure mu of this set. And this is exactly the set of points omega for which the function f takes values larger than epsilon. And if we now look what we have, we started with this, and we found as a lower bound for it this number, which is exactly what is being said in the statement of this proposition. So this proves, or this theorem, this proves the theorem Chebyshev's inequality. Replacing integral by expectation, because we know at this point expectation is nothing but the Lebesgue integral of the random variable with respect to the probability measure. So just changing the notation and terminology from the previous slide, now we have a probability, the probability that this random variable takes values larger than epsilon. This will be bounded from above by epsilon to whatever exponent alpha we want, positive exponent, times the expectation of this random variable, the absolute value of this random variable x raised to the power alpha. And this is nothing but substituting integral by expectation. And now if we do something else, we apply this estimate to the random variable y being x minus the expectation of x squared. And then we take alpha equal to 1. Then what we have here is, or let's say, to be consistent, let's not take it squared, and let's take alpha equal to 2. So here what we get is exactly the probability that this random variable y, which I'm writing here, which is x minus its expectation, that this random variable is larger than epsilon, will be 1 over epsilon squared times the expectation of the square of this random variable. And well, in probability we know what's the name that we give to this, the expectation to the square of this random variable. And we know this is denoted variance of x.